So I called this applications, and the first one is cool. It's called current balance. Basically, it involves setting up a teeter-totter inside a solenoid. On one end of the teeter-totter, you put an unknown mass. On the other end of the teeter-totter, you put a wire, and you exert a force through the wire downwards to counteract the pull of gravity downwards. And by carefully measuring the current, you can figure out the mass. As a picture, it looks like this, or as a picture, it looks kind of like this. It really is a neat setup, but in the interests of time, I have to nuke it. I'm not going to be assessing it of you. So I'm not going to cross it out, but I'm going to say, what are you going to see on your test? Cathode ray tube. Find that. Go to that page, please. The cathode ray tube revisited. TVs. Remember, Enzo, I told you that all a TV is an electron gun and then deflecting that electron with parallel plates. We actually don't do it that way. You see, the problem with parallel plates is they're lengthy. What we actually use to deflect the electrons are solenoids. Why? Oh, because solenoids are nice and compact. It let us shorten that sticking out of the back portion of the television. It let us shorten that down quite dramatically. So in actuality, we don't use parallel plates to deflect electrons in a cathode ray tube. Instead, we use solenoids. So here's a picture. And what I'd like to look at, first of all, is solenoid M. I'm going to zoom in, and I'm going to zoom in a whole bunch right there. Okay? If you look at solenoid M, the top one, the vertical one, it's possible that the current could be going, don't write this down, that way. If it was going that way, what direction is the magnetic field? Pretend to hold the solenoid in your hand, curl your finger, right hand, curl your fingers in the direction of the current. Jordan, curl your fingers in the direction of the, yeah, you got to hold it that way. So it's possible I could have a north pole there. Or I could flip the current. If I flip the current, I could have a north pole there. What I want you to write down is, it seems to me the magnetic field right here from this solenoid is either that way or that way. Write that down. We have a vertical field coming from a vertical solenoid. Duncan, depends what direction, you know. Is that okay so far? Okay. Just for the sake of argument, let's pretend that the magnetic field that the electron is hitting is pointing down. Look at the picture. Which way is the electron gun firing the electron according to the picture? Towards us. We don't deal with electrons because they're negatively charged. An electron coming towards us is the same as a proton traveling which way? So all of you point your thumbs into the page, or up here, away from you. And I said the magnetic field is pointing downwards. Which way would that deflect the electron? To the left. What if the magnetic field was pointing upwards? Which way would that deflect the electron? This is kind of counterintuitive, but it turns out, Sam, a vertical solenoid gives you a horizontal deflection. So in your notes where it says solenoid M can deflect the electron, or you can just say horizontal. This is because a magnetic field deflects the particle perpendicularly. So if you have an up-down magnetic field, perpendicularly will be left-right. What about solenoid N, the right-hand solenoid over here? It's horizontal. If you use your right-hand rule, it can either have a magnetic field pointing to the left, or it can create a magnetic field pointing to the right. My point being, the magnetic field will be either that way or that way. Let's use our right-hand rule again. Electron coming out of the page, that's a proton going into the page. Magnetic field, say if it was to the left, which way would the electron get deflected? Up. If the magnetic field was to the right, which way would the electron get deflected? Down. A horizontal solenoid gives you a vertical deflection, gives you an up-down deflection. Up slash down, or vertical. But Tanisha, the nice thing about this is, hey, I can build the solenoids very compact. In fact, we said the shorter the solenoid, the stronger the magnetic field, the bigger the deflection. This was the first step in starting to shrink down TVs. This is not, again, flat screen technology, but I'm going to assume all of you, when you were younger kids, still had televisions that had that big thing sticking out the back. Okay? So this is how, this is the TV of your youth, as we wax nostalgic.
What do they use nowadays?
I showed you guys a video of the whole flat monitor. Yeah, so that's what they do. That's one. I don't know how the organic LED things work. Samsung puts those out, and it's changing all the time because they're doing cutting edge stuff. But this is still this is certainly still what's being used in your standard ATM machine, for example. That's a cathode ray monitor because you can rattle them off for cheap. Or in most little monitors that you see in a business somewhere, you can rattle them off for cheap. Probably. Maybe it might be LCD. I have to, you know what, I gotta look into it. I may take that back now. So what kind of questions? I will, on this test, be asking you questions about the cathode ray tube. What are some questions I can ask? Oh, I have said here, show magnetic deflection. I showed you guys that a couple of classes ago. The TV and the magnet deflecting the TV, creating that big smear distortion, okay? So example 1. An undeflected electron beam strikes dead center. So when you leave this as is, it hits dead center, but then you bring this solenoid nearby. So when you put the solenoid nearby, which is giving you a magnetic, by the way, this solenoid, is it sitting horizontal or is it sitting vertical? So it's going to deflect it vertically, which is what the picture's showing, by the way. Apparently, when you just drop this solenoid in place, the new deflection is right there. What changes to the magnitude and the direction of the current in the solenoid could get it to hit at location Y? Let's talk about magnitude first. Looking at location X versus location Y, is it a bigger deflection or a smaller deflection? What do you think would give you a larger deflection? More current or less current?
More current.
Okay, because what we're really saying is the magnetic field is mu naught Ni over L. You didn't change the number, it's the same solenoid. You can change that. What gives you a bigger deflection, the bigger magnetic field? Oh, yeah, so increase the current. Yes, yes, no, no. I liked, by the way, Doug was trying to figure out what direction the current was going. We'll do that in a second as well, sure. Oh, and Doug, initially you're being deflected down. What direction are you being deflected now in location Y? How do you think you'd change the direction of deflection? Reverse the current or keep it the same? Because that reverses the field, okay? So no, yes, no, yes. Correct answer is B. By the way, just to see if we can, let's see if we can figure out what direction the current must have been flowing for X. Which way was X being deflected? Up or down? Down. So I would start out pointing my palm down, because that's the force. Which way is the electron coming? Towards us? That's the same as a proton traveling which way? So fingers, thumb into the page, palm down. What direction is the magnetic field at location in the center there? Pointing to the? Right. See, now we're reversing. This has a magnetic field pointing that way. So I'm going to just, don't write this down. I'm going to clutter up the diagram. Originally, the magnetic field was pointing that way. Magnetic fields always point from what to what? Which means there must have been a little south pole right there. Okay? What would give you a south pole right there and a north pole right now? I'll hold the solenoid. You know what? Initially, the current must have been curling over the top towards us. I can reason my way. It's like a 4-step reasoning, but I can reason my way there. Which would suggest that afterwards, the current was traveling, curling underneath the solenoid away from us. Let's see if we can reason that. Let me erase this, let me erase this, let me erase this. So if we got deflected up, the electron got pushed up, I would point my palm up. Normally we did the palm thing last, but this time that's what I know. I'll start out with the palm thing. Electron coming towards me, same as a proton traveling away from me, so I'll point my thumb into the, you know what, there's my deflection. Oh, my fingers are pointing to the left. To get Y to occur, you need a magnetic field pointing that way. Magnetic field lines always point from what to what? From north to south, so there must have been a north pole right there. And yeah, that does work. That would be also a nice kind of a using principles of physics type of a question as well, right? What else? With the electromagnet turned off, electrons in a cathode ray tube strike the center of the screen as shown. When the electromagnet is turned on, where will the beam now strike the screen? Look at the solenoid. Is the solenoid vertical or horizontal? So a vertical solenoid is going to give you what type of a deflection? So you know what? I'm going to cross out answer 1 and answer 3. It's not going to deflect it vertically. Hey, and now I've turned it into a true-false guess question. No, I'm not going to guess, Jordan. I can do better than that. I've got to zoom in again. This isn't a great photocopy, and I apologize, but I think if you look really close, it seems to me the positive is right there, and I think if you look really, really close, it's curling over to the right in the solenoid, isn't it? Is your photocopy clear enough that you guys can see that or not? Okay, so I'll try and find a better one for next year. Hey, these diagrams don't show up. You know what? Google has improved. Maybe I can find a better diagram. I'm going to tell you that it's curling over that way. So the first thing we want to do is we want to figure out what direction the magnetic field is, where the electron is. How? Use our right-hand solenoid rule. So hold the solenoid in your hand, right hand, and curl your fingers in the direction that the current is, which means, oh, I don't want to hold it this, I would have to hold it this way, right? So which way is north? That's south. Magnetic field lines always point from what to what? So what we're really saying is the magnetic field line is going right here. It's right where the electron is. It's pointing up. Which way is this electron traveling? We don't deal with electrons. Again, on your test, though, it's often going to be an electron because although our right-hand rule works for positive charges, it's electrons that are much easier to fire and move, and so just be cautious. Keep an eye out for that. So an electron coming towards me, same as a proton traveling which way? So point your right thumbs away from you, into the page. Which way is the magnetic field? Up. Doug, which way is your palm pointing? Is the answer 2 or 4? 4. Okay. So one neat application of the right-hand rule, TV, which I think you would argue all of you are a TV generation. Most of you would have a tough time living without it. I'm sure you'd adjust, but most of you, when you think TV, you think happiness, joy, and comfort. Some of you, when you think TV, also think, oh, special friends, right? Okay. 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 There's another application that in my mind actually is even cooler and in some ways more useful, and it's the electric motor. The electric motor. Okay? I had a great animation that showed how this worked, and just yesterday I found out that it was written in such an old version of Java that my computer, for security reasons, won't run it anymore. So I found another one. Look up. Here's an electric motor. Sorry, a really, really simplified electric motor. Let me show you the top view. Okay? In an electric motor, what you have is a wire. Now, this is the simplest case. It's a single wire. In real life, what you do is you have a coil of wires, because every time you add one wire, you double the force of the electric motor. You want to make the electric motor 100 times stronger? Add 100 wires. You want to make the electric motor 1,000 times more powerful? Add 1,000 wires. But here's the simplest case. And what you do is you send a current through it. Positive right there. Positive right there. Positive going this way, going this way, going this way. So if you notice between A and B, it's positive going away from us in the wire. In between C and D, it's positive coming towards us, currents coming towards us. Okay? Then what you do is you put it inside an external magnetic field. That's the yellow lines. Can you see them okay? I didn't show you, but you can imagine that there's a big North Pole magnet right here and a big South Pole magnet right here. And you can do the magnet one of two ways. You can put permanent magnets, and some of the small electric motors have permanent magnets, or you can use solenoids. Big electric motors have solenoids. What's going to happen? Let's look at between A and B. Which way is the current moving right where I've put my cursor away from us? So I'm going to point my right thumb kind of into the page. Which way is the magnetic field from those yellow lines? So if I point my fingers to the right, the left-hand side of this piece of wire is going to feel a force in which direction? Downwards. Hold that. Look at location C and D. Which way is the current traveling in location C and D? Towards us. Which way is the magnetic field? Still to the right. What direction will C and D feel a force? Up. The right-hand chunk of wire is going to feel a force up. The left-hand chunk of wire is going to feel a force down. If you push up on one side and down on another side, you're going to get it to spin. This is how electric motors drive cars, drive elevators. You're going to get it to spin. Now, the problem is, if this was all I had, as soon as AB got to this side, now I would have current flowing away from me on this side, magnetic field here, and it would feel a force up. You would have this. Spin stop! It would cancel out the spin. So we have to get clever. What we have to do, Tanisha, is come up with some way that we always have the current moving upwards on the left-hand side and always have the current moving downwards on the right-hand side. Now, from alternating current, that's really, really easy because the current flip-flops automatically. But most of our electric toys run from batteries and have direct current. So we have something that we call a split ring commutator. Say what? I've deliberately kept it hidden. Now I'll show you what it is. Okay? Right there. We have a metal circle with tiny gaps. You can kind of think of it like a hamburger bun, and where the patty is, we've removed the metal, if you're looking at it from an end view. How does that work? Well, watch what happens. So it's going to start to spin. Okay? Spinning, 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 spinning. Now, right here, there's no more current flowing, but its momentum keeps it going for a little bit. And now, and now if you look close, we're now in contact with this one, but this one, which was once taking negative current, now has positive current. Watch it again. Spinning, spinning, spinning. Again, you'll notice the current is flowing positive, still, and now in DC, it's flowing away from us. It was flowing towards us. Now in AB, it's flowing towards us. It was flowing away from us. Keep going, keep going, keep going, keep going, keep going, keep going. It coasts for a little bit. Right here, there's no current flowing through the wires at all, but its own momentum will keep it going so that it will, well, you know what? Let's hit play. Oh, hang on. Start back here, Mr. Dueck. Let's hit play. Hang on. Reset. Oh, there's the magnets. I knew there was a way I could get, there's the big magnets. I knew there was some big magnets somewhere. Play. Okay. So I'm going to see if I can pause it at certain times, right about there. This is when it's feeling the maximum force. So looks like I have current going that way, magnetic field that way. This is getting pushed down. Current coming towards me, magnetic field, coming towards me, magnetic field that way. This is getting pushed up. There's the spin. If we didn't have that little gap right there, which automatically from a direct battery was able to just flip the current and always keep it going to the same side, this wouldn't work. Oh, and what we have are just, the way we keep these in contact are just with some wire brushes so that they're conducting the current, Sanj, they're conducting the current into that little metal hoop, the split ring commutator, but there's not much friction so that it can rotate quite nicely. Let me hit play again. Okay. Heck, I'll even give you a little graph. I think I'll give you a little graph versus, Maybe I won't. Oh, there we go. Do that. Here's the magnetic force. It peaks, it goes to 0. It peaks, it goes to 0. But you know what? Once it goes faster and faster and faster, it really smooths out to a fairly constant force. Does that make sense? I hope. This is how electric motors work. No, it's not. There's a real problem. The problem is if you shut the motor off and it happens to stop exactly right there, it won't start again because there's no current conducting, there's no force. Oh, by the way, even if there was current going, you'd have current coming towards me, magnetic field this way. Well, it would get pushed up, which doesn't exactly cause it to turn. Or if the current was going away from me, magnetic field that way, it would get pushed down, which again doesn't exactly cause it to turn. So this was the early prototype, like back in the 1880s, back in the 1890s. And now what they actually do, they're clever. Instead of having a rectangular coil of wires, they build it in an equilateral triangle. And so if you think about it, what that means is there's no way you can ever stop without at least there being some force to get it to spin again. There's no way you can get a force of 0. They have, I guess, 3 coils of wires at 120 degree angles to each other. Kind of clever. Enzo, is that okay? Let's walk through the lesson now. So here's what we're saying. Figure 7.28 shows a simple one-turn coil motor on direct current. So here's a picture. I've given you kind of an end view and a top view. So in this particular system, we have current going up the page, magnetic field going that way. This side will get pushed down, this side will get pushed up, and it'll start to spin. And as long as we have a gap there, then when it gets to the gap, its own momentum will keep it spinning, and then the current will continue to flow, because this will be on this side, this will be on that side, but it'll always continue to flow in the same direction, giving you the same spin. Hey, you put 2 wires in there, you'll have twice the force. You put 3 wires in there, you'll have 3 times the force.
Who came up with this?
Initially, Michael Faraday was the first one to come up. He had a different design, but he invented, Michael Faraday is the father of all electricity. He invented the electric motor and also the electric generator. By the way, you'll learn in a couple of weeks, that's also a generator. It turns out if you supply current, you can get motion. If you supply the motion, you'll get current. So a hydroelectric dam supplies the spin, and it turns out you'll get current coming out the other end. The same way as if I supply current on this end, that'll create the spin. So it was not a big leap in thought, but yeah.
Is there a reason why we all have gas cars instead of electric cars? Like, did gas kind of just...
Lobbyists. Battery technology. Battery technology. If we have our breakthrough in battery technology, we're happy campers. We really are. Electric motors, more efficient. They go like stink. Like people, oh, electric car. Actually, no. I've showed you the guys that little video. Pause for a second. Okay, so you can think of it this way, looking on the end or here. And I wrote here, notice the importance of the split ring commutator. That's what they call it. The way that I can, from a direct current source, somehow flip the current in the wires so that it's, because the wires themselves flip, so I can always have current going in the same direction on the left-hand side and the same direction on the right-hand side. Okay. Here's a typical laboratory demonstration motor. We call these brushes, and they literally are little metallic brushes. Give me about 5 minutes. I'm almost done. Okay. For a nice animation, sadly, this is the lovely animation that is now dead, and I can't get it to run anymore. Okay. So, electric motors come in all sizes. Some are very tiny and drive toys. Others are huge and drive trains or buses. You'll find electric motors in toy trains, automobiles, clocks, wheelchairs, streetcars, can openers, cement mixers, furnace fans, robots, many other devices. I mean, anything that you plug in and it gets something to vibrate has an electric motor. The PlayStation joysticks, that because I had a transparent one, that vibration, there's a spinning motor in there that just has a weight off-center, and so that weight, just because it's off-center, causes the joystick to feel like it's vibrating, feel like it's moving. Your cell phones, I need to find out, I think the vibration comes from an alternating solenoid magnetic field, not a spinning off-center electric motor, but I've never looked into that. It's on my list of things to do. Elevator motors, fans that you plug in, clocks, that's an electric motor, it moves in a circle. And by the way, now you're also understanding why so many of our electric devices move in a circle. It's why so many amusement park rides, which run on electricity, move in a circle. Okay? It's an easy, I mean, we can scale it up as big as we want, just about within reason, we can scale it up. So that's the electric motor. Now, listen closely, this is important, Enzo. I will not be testing you on the electric motor on this test, but I'll be hammering it in the next test, and so I always plant the seed. I will be testing you on the cathode ray tube application. What's your homework? I'm going to be giving you a take-home quiz, and then I'm also going to be giving you the big electromagnetic forces review. You really want to do it before you write the test.